Hate it when it does that. Okay, somebody tell me at home that you can see my Moodle, my slide presentation, stuff like that.
Yeah, we can see it.
Awesome. Okay. So in this week's, you've got a lot of videos here. Three-phase transformer, closing a delta connection. Pay attention to that one. There is some questions on that. Three-phase transformer calculations. We will be doing that one right there. We'll probably watch that one after we go through the PowerPoint. A 4-wire Y connection. Anybody have a idea of what that's going to look like? Three hots, a neutral, and equipment ground, basically. Basically what we went over a little bit 2 weeks ago with our Y connections, right? Got a Y connection, so that's going to be it right there. Three hots, 270 or 480, 277 will be a Y connection. 208, 120 will be a Y connection. Okay, know what those are. There is some stuff in your uglies book as well that'll go over some of these transformer connections and calculations and stuff, so know where those are. A high leg connection, we'll kind of go over that. I won't go over the video, but we'll go over that. And an open delta connection. I won't go over that. So you've got some videos there. We're probably going to watch this one right here, the 3-phase one. And then we're going to do a couple calculations, and then we're going to jump into Mike Holt and transformer calculations on the primary side. And okay, so for now, we're going to go over this. Three-phase transformers. So in this unit, after studying this unit, you should be able to discuss the operation of three-phase transformers. Connect three single-phase transformers to form a three-phase transformer bank. Okay, pretty easy. How many of you have looked out on a power pole from the utility and see three individual transformer buckets? Okay, basically three individual transformers. And if you look closely at them, you should be able to tell if they are hooked in a delta or a Y configuration. Okay. What would be a dead giveaway if it's in a Y connection? Nope, you can't see that clear up on a 30-foot pole. Anything else? I think it might show a picture. Well, let's see. Let's look in the book. I might show you in the book here. So page 674. Figure 28-7. That's what I'm talking about. I got three transformer tubs sitting on top of that pole. How am I going to tell if those are connected in a Y or a delta? Where the wires are going is part of it. What's that going to tell me? Yeah, basically it does. So if you look at the figure right above it, it's going to be either connected real similar to that, two of them tying together, two of them tying together, two of them tied together, or you're going to have all three of them tied together at one location. Okay, that's how you're going to tell. You can trace those wires and tell if those are in a delta or if they're in a Y. Okay, just by looking at how the wires go in between them all. Okay, so that's how you're going to be able to tell. So calculate voltage and current values for a three-phase transformer connection. Everything right there is pretty much going to be the same that we did 2 weeks ago with the single-phase transformers, okay? Calculations, the ratio, all that's going to be real similar. Some of them is just going to be a little bit higher, okay? Connect two single-phase transformers to form a three-phase open delta connection. Okay, we'll go over that a little bit here in this presentation as well. After studying this unit, should be able to discuss the characteristics of an open delta connection, discuss different types of three-phase transformer connections and how they are used to supply single-phase loads, calculate values of voltage and current for a three-phase transformer used to supply both three-phase and single-phase loads. Okay, three-phase transformers used to change values of three-phase voltage and current. Three-phase power, most common way in which power is produced, transmitted, and used. So typically, how many of you have been down the freeway, down past Downey, Malad into Tremont? And you see those power lines off to the side of the road. They run all the way down. They basically run from a transformer, substation in Downey all the way down to North Ogden is where they run. Okay. They follow the freeway all the way down in through Tremont. Then they follow it over into Brigham City, except they kind of go away from the freeway over onto the hillside, the mountains, and then go down that, and they come out and they go over to a substation, big old substation down by, anybody know where Smith and Edwards? Anybody heard of Smith and Edwards? Hopefully you have. Great big fun store. So then they go down there. Okay. If you look at it, you can see phases A, B, and C, or 1, 2, 3. You can see what they call their ground, which would be underneath it. Okay. They don't have well, their neutral, or our neutral, is their ground. Okay. I think we've talked about that a little bit. So you can see how those are transmitted in 3 phases down through there. Understanding of connections is essential. So 3-phase transformer, here you go, kind of a basic construction of a 3-phase transformer. 3 single-phase windings on a single core. As you can see, got 3 windings on a basic core right there. Here's our 3-phase transformer connection. Here's our Y. Obviously, it looks like a Y. Here's our delta. Anybody remember why it looks like a delta?
Because of the Greek letter.
Delta. Yep, very good. Okay, so L line 1, line 2, line 3, line 1, line 2, line 3, or vice versa, however you want to do it. Where would the neutral point be on the Y system? Anybody tell me? What's that? Where would I derive my neutral or grounded conductor on that Y transformer? Middle. Right there. It'll come off right there and go to our grounding electrode system. And that's where we're going to bond everything right there, except we do not do it on the primary, we do it on the secondary side. Where would I derive my neutral in a delta connection? What's that? On a corner grounded system, it would be on a corner ground. Typically, I'd ground this one and take it down, and that'd be what they call a corner ground. Don't see those very often. More often than not, it's going to be in the center of one of the transformers. It'll be a center tap, and it'll come down and it'll hit ground there. Now, when I do that, we'll probably talk about this a little bit later. When I do that, what would be the voltage from my center point? Well, we'll just worry about that later because I believe it will talk about it. Don't want to get ahead of the game here. So this is how I learned when I went through school to tie my transformers together. Can anybody tell me which one of those, top or bottom, is a delta connection? Just by looking at that figure right there. No. The bottom is a delta. Line here, and then that comes all the way around, ties into that one. Would that not be a delta? Top one is a Y because I got H2, H2, H2 all tied together. Right there. All three tie together in one point. Then I got L1, L2, L3. Okay. If you were to draw it like this, which is what I learned how to do it to figure it, and you can do it that way. There's another way of doing it that I won't go into, but there's another way you can do it just as easy as looking at it like that. Connection should be checked for proper polarity before final connection and applying power. Testing for the proper transformer polarity before closing the delta. We kind of went over that 2 weeks ago, right? Closing a delta. Same thing on this one. Calculations. Only phase values of voltage and current can be used. Is that what it said 2 weeks ago with single transformers? Use the phase values, right? Same thing with this one. We use the phase values. Refer to these examples because they will give you the proper answer. Okay, an open delta. Here's our open delta, L1, L2, L3. We don't have a side here, right? Single phase loads, 3-phase transformer connections often used to supply single phase loads, trends to unbalance the system. Okay, you do not see that a lot, but if you do, you're going to have an unbalanced system, and you will have, well, I can't say that because you will have unbalanced loads on a Y system if you're not careful. Additional considerations, an open delta connection applying a single phase load there as well. Okay, so here's my open delta. I got a high leg. I think they're using that as my neutral. Tap is for a neutral. That'd be my high leg. 120 volts to neutral here. 120 volts to that one there. 208 phase to phase here. Phase to phase here would be I believe it's 240. Maybe it's 208. I can't tell. Should be 240. No, that's going to that one. So on this, let's see, 20. Shows it on that one, 28-6. So 3-phase open delta transfer supplying both 3-phase and single phase. So phase to phase, I'm going to have 208, no, 240 volts. 240 volts phase to phase. When I go this phase right here to this neutral point, I've got 120 volts. When I go this phase to that neutral point, I've got 120 volts. But if I go from this leg up here down to that neutral point, I'm going to have 208 volts. They call it a high leg. Okay. If you're in your code book, it tells you if you have a high leg, it must be identified by what color? What's that? Nope, not blue. Nope, not red. Not yellow.
What?
What'd you say? Orange. It will be orange. Any high leg must be identified by orange, which comes to be a problem because what do they use for a 480, 277 color code? Brown, orange, yellow. Is that a code requirement? Brown, orange, yellow, black, red, blue. That is not a code requirement. That is a standard amongst the electricians. I could use black, orange, purple to color code my phases if I wanted to. Okay, but the standard amongst the trade is black, red, blue, white for a 208 120 system. Black, red, blue, white for a 208 120 volt system. A 480 277 is typically brown, orange, yellow, gray. Okay, there have been a few instances where certain localities, municipalities, cities, contractors, where they, if it's a 480 277, they will remove the orange and put purple there. Does not matter. When I was the first apprenticeship, purple and pink were used for travelers. Where do I use travelers? 3-way and 4-way switches. Okay, that is not code, it's not law, it's just, that's a color that we have, okay? But typically a 480 277 is brown, orange, yellow with a gray neutral, okay? So, but if I've got this high leg, 208 volt, that must be orange. And where do I land it in my panel? A, B, or C phase? Anyone at home know that one?
B.
B phase, very good. I think it talks about that in here somewhere. It doesn't. It should, but I can't remember where it talks about that. Okay. So anyway, so that's where we call a high leg. Single phase loads, additional connection considerations of voltage values, load conditions, and calculating the neutral current. If I'm using this type of a connection, my neutral current, you have to be cautious of it. If I have a really high neutral current or unbalanced load, that neutral might have to be oversized. Okay. So pay special attention if I've got an open delta or any type of delta connection with a neutral and I'm supplying a lot of unbalanced or neutral loads on there. Okay. Here's a closed delta with a center tap. I'm still gonna have that high leg there because between that leg there and that neutral is going to be a higher voltage than if I go this phase to neutral and this phase to neutral. Okay. But phase to phase, I've still got the same volts. Okay. Closed delta without a center tap. Where would I use a closed delta without a center tap? Why would I not need a center tap or neutral connection there? All three phase loads, motor loads, whatever, okay? Any type of three-phase load that does not need a neutral, I do not need a center tap on that delta, okay? Idaho Power and I believe Rocky Mountain Power are doing away with pretty much all delta loads in the agriculture. They're going to Y. I believe all throughout the Aberdeen, Blackfoot area for Idaho Power, they are removing all their delta services and going to a Y. Here's your delta Y connection with the neutral. There's our neutral connection right there. Phase to phase would be 208 or 480. Phase to neutral would be either 277 or 120. Okay, and there's my Y load. Here's that is not a delta Y connection with neutral. That is a Y to Y and a Y load. So they identified that slide wrong. Delta Y, that'd be a YY. Okay, this is kind of how I grew up, went through the program with the lines up here. I got A, B, C phase, and then I would also have a neutral line up there. One of those would, the fourth one would say neutral. Okay, this is only a T connection with two transformers, but that's similar to what I did when I went through school. You had A, B, C with a line for your neutral, and then you would take your lines to each individual one corresponding. Okay. Here's this one was 13.8 volts down to a 480. Okay, this is a 24,000 volts down to 240 volt. Just showing you the T connected transformer with the same voltage rating, how to do those. Okay. Here's a voltage vector relationship with the T connection. Just shows you how that all works with the T connection. I have never seen a T connection. I don't know if that's something the power company does on their end, or I have never seen one out in the field when I had the tools on or when I've been doing inspections. I don't know a lot of places where this will come into effect. If you read it, it might tell you where some of those come into effect, but like I said, I have not seen one. You might want to go ask your journeyman and your bosses if they have ever seen one. So another T-connected transformer provide a 3-phase 4-wire system. Showing it right there. A Scott's connection. I've never seen one of those used to convert 3-phase power into 2-phase power using 2 single-phase transformers. Again, I have not seen one of those, but I'm not saying they're not out there. A zigzag, primary used for grounding purposes to ground a transformer. I think the power company uses that more than we do. 6-phase transformer connection. Okay. 6-phase transformer connections are often used to supply rectifiers for converting AC voltage into a DC voltage. Okay. Again, to me, this would be something if you've got a 3-phase solar farm that you might come into play on that, but I have not seen those either. A double delta connection, 2 delta connections are formed with 2 secondary windings for equal voltages. So there's another one you can go through right there. A double Y. So you just basically got 2 transformers on each primary transformer, if that makes sense. Okay. So with that, constructing a 3-phase transformer constructed by winding 3 separate transformers on a same core material. Single-phase transformers use a 3-phase transformer bank, calculate 3-phase transformer values. Rules for 3-phase circuits and transformers must be followed, that we talked about 2 weeks ago. Values must be based on the phase values, not the line values. Total power output of a 3-phase transformer bank. The sum of the rating of the 3 transformers in open delta can be made using only 2 transformers. An open delta, you're only getting 86.6% of the total power of the 2 transformers. It is common practice to center tap one of the transformers in a delta connection for your single phase loads. Therefore, where you would get the high leg, here's the requirement. NEC requires that a high leg be identified by an orange or by tagging it, and it must be the B phase. Center connection of a wall to provide a neutral connection for 3-phase transformer connected as a YY unless the incoming power line contains a neutral conductor. Okay, that's why you usually don't see them in a Y on the power side. T connection, Scott, zigzag. Just pay attention to those. Any questions on those? And the 6-phase and the delta or double Y connections. Okay. Let me know if you can hear this at home. Please say something, don't comment on it. Can you guys hear that at home?
Yeah, we can hear it. Well, I can hear it.
Awesome. Great.
To determine the voltage and current values in a three-phase transformer connection, you need to apply Ohm's law, three-phase rules concerning voltage and current relationships in Y and delta connections, and rules governing the voltage and current relationships in transformers. In this example, a Y-delta connected three-phase transformer is supplying power to a three-phase Y-connected load. The load has an impedance of 4 ohms per phase. The transformer primary is connected to 12,470 volts, and the secondary voltage has a line value of 480 volts. The first step in finding all the missing values is to find the values associated with the load. Since the secondary of the transformer is supplying a line voltage of 480 volts, the line voltage of the load will also be 480 volts. Now that the line voltage connected to the load is known, the phase voltage can be determined. In a Y connection, the phase voltage is less than the line voltage by a factor of the square root of 3. 480 divided by 1.732 equals 277 volts. Each of the phase resistors in the load has a voltage drop of 277 volts. The phase current can now be determined using Ohm's law. The phase current is equal to the phase voltage divided by the phase impedance. 277 volts divided by 4 ohms equals 69.25 amps. In a Y connection, the line current and phase current are equal. Therefore, the line current supplying the load is 69.25 amps. Since the transformer in this example is supplying power to only one load, the secondary line current is also 69.25 amps. In a delta connection, the phase current is less than the line current by a factor of the square root of 3. 69.25 amps divided by 1.732 equals 39.98 amps of phase current in the transformer secondary. The phase voltage of a delta connection is the same as the line voltage. Therefore, E phase of the secondary is also 480 volts. The next step is to determine the phase voltage of the transformer primary. In a Y connection, the phase value of voltage is less than the line value by a factor of the square root of 3. 12,470 volts divided by 1.732 equals 7,200 volts. The voltage across each of the primary phase windings is 7,200 volts. When determining the values of voltage and current between the primary and secondary windings of a three-phase transformer, it's important to understand that all transformation takes place between the phases of the transformer. The phase windings that comprise the Y-connected primary of the three-phase transformer bank are the high-voltage windings of the three single-phase transformers. Likewise, the phase windings that comprise the delta-connected secondary of the three-phase transformer bank are the low-voltage windings of the three single-phase transformers. In this example, the primary has a phase voltage of 7,200 volts, and the secondary has a phase voltage of 480 volts. The turns ratio can be determined by dividing the higher voltage by the lower voltage. 7,200 divided by 480 equals 15. This transformer has a turns ratio of 15 to 1. This indicates that there are 15 turns of wire in the primary winding for every 1 turn in the secondary. Like any step-down transformer, the primary current can be calculated by dividing the secondary current by the turns ratio. The phase current of the Y-connected primary can be found by dividing the phase current of the delta-connected secondary by the turns ratio. 39.98 amps divided by 15 equals 2.66 amps. In a Y connection, the phase current and line current are equal. Therefore, the line current supplying the primary is 2.66 amps also. All the missing values for this transformer and load have now been determined.
Okay, so pretty similar to what we did a couple weeks ago, right? Okay. Trying to find one thing here and I'm not having luck at it in the code book. Okay, in your code book, 110.15. One 10.15. That's where it tells you on a 4-wire delta connected system where the midpoint of one phase winding is grounded. Only the conductor or bus bar having the higher phase voltage to ground shall be durably and permanently marked by an outer finish that is orange in color or by other effective means, such as identification shall be placed at each point on the system where a connection is made if the grounded conductor is also present. Okay, orange in color. In a panel, I think if you were to go to the panel board, it tells you there. Let's see, for uh 408 dot, what is this? 408.3 F1. A switchboard, switchgear, or panel board containing a 4-wire delta connect system where the midpoint of one phase winding is grounded shall be legibly and permanently filled, marked as follows. Tells you how to do it. Somewhere it tells you it's gotta be the B phase, but I don't see where it's telling me that.
Hey Todd,
Yep,
on the NEC 408.3E1, it says requires that in a four-phase delta connection system, the phase with the higher voltage to ground must be connected to the B phase position on the panel board bus bar.
I was in 408. I just didn't read far enough then.
Yeah, 408.3E1.
Oh, yep. I knew it was in there somewhere. I was looking down at F for the high leg identification, but phase arrangement, that makes sense. Okay, I knew it was in there. Okay, so, who was I getting some text messages from? Just a second, hold on.
Thank you. Do you, Todd? Do you want us to mark 408E1?
If you want to, that's fine.
Okay.
Okay. So with unit 28, you're gonna have a lot of stuff there. But a lot of it is real similar to what we talked about 2 weeks ago, other than the different types of connections and stuff like that. I do want to do a couple of those calculations real quick. So if you go to the practice problems, 1 and 2 refer you to figure 28-14, which is about the middle of the unit. 3 and 4 refer you to the figure right there between them, figure 28-41. Let's solve for, I think it's just the 4 questions, yeah, for this one. Let's do number 4, solve for all those values. Now again, it's real similar to what we did a couple weeks ago. So the load on number 4 is, or the impedance is 3 ohms. So use those to solve all those formulas right there. I will give you 22 minutes, which would put it at 7:30. So 7:30 we'll come back unless everybody's done before then, but let's start with that to solve number 4.
Hey, Todd.
Yep.
Hey, what page did you say?
I'm on page 699 in the Delmars.
Okay, thank you.
Yep.
Todd, figure 2841 is question 4, right?
Correct.
Okay, thank you.
Preston Wheatley, John and Riker, where's your cameras? Thank you. Okay. So let's go over this one, number 4. Whether you're done or not, that's fine. So we know the primary is a delta. It gives us a line voltage. We know our phase voltage is what?
23,000 volts.
23,000 volts. It's gonna be identical, okay? So with that, there's not much more we can do till we get to the secondary. We go to the secondary. We got a line voltage of 208. Our phase voltage is gonna be what? And a Y.
120.
120. How did you get it?
You divide 208 by the square root of 3.
1.732. Very good. So we got the secondary voltage, phase voltage of 120. Okay, so my load is a delta. So I know my line voltage is going to be 208, right? Line voltage 208 from the secondary over to the load 208. My phase voltage is going to be what?
Same.
The same, 208. So now I take that phase voltage of the load 208 and I divide it by 3 to get my amps, right? Is that my phase amps or line amps?
Line amps.
Phase.
Phase, because I'm using my phase voltage. Phase voltage and my resistance or impedance will give me my phase current. What do you get? 69.33333 amps. Okay, so from 2 weeks ago, I knew if I had a phase current and my voltages were the same, my phase current or my line current is going to be larger or the same. Or smaller. Anyone? Logan Reynolds, you know the answer to that one?
What was the question?
My line current is going to be larger, the same, or smaller than my phase current.
Larger, right?
Larger by what?
By double.
Not quite. What's my formula?
Go back and look at it real fast. You times it by 1.73.
0.732, very good. So you get almost double, 120.085, correct?
Yep.
Okay, so I carry that back to the secondary side of a line volt or line current there. Line current of 120.085. My phase current on my secondary, same, greater, smaller?
Same.
Same. Kind of funny, I've got a phase voltage of 120 and a phase current of 120. Pretty darn close, right? Okay, so with that, how do I find my ratio?
The higher voltage by the lower voltage, isn't that?
My primary phase by my secondary phase, correct?
Yeah, yes.
Okay, what do you get, Xander?
191.66.
One.
1, yeah. Yeah.
Very good. So my ratio 191.667 to 1. So what does so do I take that to find my phase current or my line current? Joseph Hale, what do I find with that? Phase current or line current?
Wouldn't it be your line current?
No, it's my phase. Always use phase values. Okay. So I take my phase current on the secondary, 120.085, multiply or divide it by the 191.667. Who was that?
Deacon.
Deacon. You said divide, very good. What do you get?
One second, I hadn't done it yet.
Okay.
What did you get for the secondary phase current?
120.085.
Uh, 0.626.
Yep, 0.626 something. I got 0.627 amps. So what would be my line current? Greater, smaller, and by what percentage? Or factor?
Greater.
Greater by what, Ben?
I would say like 50%.
No, there's something you multiply it by. What is it?
You multiply it by the square root of 3, so 1.732 to
32, yep.
get your line.
What do you get?
1.08.
Okay. Any questions with that? Like I says, it's real similar to what we did a couple weeks ago, right? Any questions at home about that stuff? Okay, so the rest of that, I'm gonna leave that up to you to watch those videos. If you need extra stuff, go through those review questions in the back of that unit. But for now, I want to take you to Article 450 of your code book. And I'm going to share a different screen. Okay, everybody can see this slide presentation at home? Someone tell me?
Yes.
Okay, so part C of this is transformers. Okay, so in this section, in this part C, you'll cover how to size the primary protection only of a transformer using table 450.3b and the applicable notes. In addition, we will also cover how to size the transformer secondary conductors based on the secondary overcurrent protected device they terminate into in accordance with 240.21c. Who's got 240.21c and wants to read it, please? Two 240.21c.
Todd, is this the right chapter? Can you see that?
I can because when I shared, I lost everybody's picture in the.
Oh, okay. I'm trying to look for that.
It's not, we're not in the Delmar's book anymore. We
Oh.
are.
Yeah, I'm in the code book.
Okay.
I got that one, Todd.
Okay, read that for me.
240.21C, transformer secondary conductors. A set of conductors feeding a single load or each set of conductors feeding separate loads shall be permitted to be connected to transformer secondary without other current protection at the secondary, as specified in 240.21C1 through C6. Section 240B shall not be permitted for transformer secondary conductors.
Okay. So we're basically gonna do one, protection by primary overcurrent device. Conductor supplied by the secondary side of a single phase transformer having a 2R single voltage secondary or a 3-phase delta delta. Actually, we're not gonna do that one. We're not worried about that one. So I gotta use 1, 2, 3, 4, 5, or 6. Okay, and they're going to give it to us as we go through this. Hate it when somebody calls in the middle and I know who it is and I don't want them to talk to them. Okay, so transformers having secondary voltage not exceeding 1,000 volts with primary overcurrent protection only must have the primary overcurrent protection device sized in accordance with the percentages contained in table 450.3B. So everybody go to their code book in article 450.3. Should see a table there. And we want table 3B. It's found on, if you're in a standard code book, in the 23 code book, it's 70-374 is the page number. If you're in the handbook, I do not know. What page is it? 590. Okay. The title of this table, maximum rating or setting of overcurrent protection for transformers 1,000 volts and less as a percentage of the transformer rated current. Okay, so on the left side, I got protection method, primary only, and primary and secondary protection. Right now, we're going to be dealing with primary only. Currents of 9 amps or more, I multiply that answer by 125%. Currents less than 9 amps, I multiply my answer by 167%. Currents less than 2 amps, I'm allowed 300%. Okay. And then it goes into the secondary protection if I want there. Okay. And then there's some footnotes underneath there, 1, 2, and 3. Okay. So basically right here, B, primary protection only, primary currents less than 2 amps, 300, 2 to 9, 167, more than 9 amps, 125. And then there's note 1, transformers having a primary current rate of 9 amps or more are permitted to use the next size up rule when 125% of the primary current does not correspond to the standard rating of a fused or non-fused circuit, non-adjustable circuit breaker listed in 240.6A. So what does that say? If I'm using 125% and say I get 32 amps, what size breaker can I use or fuse? You have to go to article 240.6A, find your standard ratings for fuses and circuit breakers. Is there a 32 amp size fuse or circuit breaker? What are my standard sizes? $30 and $35, right? I'm right in the middle. So according to that, I'm allowed to go up to 35. Okay. That's if I'm at 9 amps or more. I'm allowed to go to the next standard one. If I do not have 9 amps or more, I have to go down. Okay? So here's a formula. Here's a question. What is the maximum primary only overcurrent device size permitted for a 750 volt amp 480 to 240 volt transformer? Okay. So what are my steps? Well, let me show you. Okay. I've got a 480 volt primary hold on, got lost all my books here. So right here, let's go back one. 750 volt amps, power in, power out, right? Always remember that, power in, power out. I've got 750 volt amps coming into it, 750 volt amps going out of it. 480 to 240. 480 right here, 240 right here. So first I got to find my amps, right? So how do I find my amps? I take the 750 volt amps, divide it by my volts, I get my amps, right? Primary current 750 divided by 480, I get 1.56 amps. Okay. So we are only dealing with currents less than 2 amps. Is that what the question said? Current less than 2 amps. Do I got less than 2 amps? Absolutely. So going to that table, in table 450.3b, do I multiply it by 125, 167, or 300? 300 less than 2 amps, so I can go 300%, right? So if you're looking at the slide, it tells you right there, 300% times 1.56, I get 4.68 amps. Am I allowed to go up or down? Less than 9 amps is what the thing said, right? Go back 2 slides. No, 9 amps or more, next size up. Note 1 for rounding only applies to primary currents 9 amps or more. So I've got to be, what's my standard size fuse in table 240 dot, was it the 240.6? Go to the informational note or the one right below it for additional standard sizes. A 240.6A 136. So if I've got 4.68, what size fuse do I have to have? 3. Can't go up because I'm not at 9 amps. Note 1 applies only to 9 amps or more. Okay. So if I go to here, I'd be able to set my fuse at 4.68 or less. Answer is B. Okay. So any questions there? It's kind of confusing. It's kind of tricky. So go back to 450, lost my page. Note 1. Where 125% of this current does not correspond, so I can only use that. So I cannot use anything more than what I calculate at, right? According to that one. Any questions with that? Does that make sense? Kind of hard to follow, but. So that's just my primary current. That's a small transformer. Okay? That's a small transformer. 750 volt amps, that's small. Okay, the next question. Now I'm dealing with the other one, currents less than 9 amps. So basically anywhere from 2 to 9 amps. Table 2 450.3b. What is the maximum primary overcurrent device size permitted for a 2 kVA 240 to 120? Okay. 2 kVA is what? 2000 volt amps, right? Move your decimal, K, 2000. So here's how you solve it. 9, A, B, C, or D, 9.8, 11.3, 13.9, or 15.1. 2000, I'm looking right here. 2 kVA divided by the 240, 2000 divided by 240, I get 8.33. Now go to my table. Less than 9 amps, I multiply it by 167, right? 167%, I get 13.92. Am I allowed to go up? No, I'm still not at 9 amps or more at 125%. Right? Note number 1 is only on currents of 9 amps or more and 125%. Note 1, where 125% of this current does not correspond to the standard size fuse or non-adjustable breaker, a higher rating that does not exceed the next higher standard shall be permitted. So I have to be 13.9 or lower. Standard fuse would be 10 amps, right? According to 240.6. So I'm most likely going to put that on a 10 amp fuse or 10 amp circuit breaker, and hopefully it holds. Okay. Again, small transformer, 2 kVA, not very big. The big ones that you typically see that are about 2.5 foot or 3 foot by 3 foot, the big ones you see in commercial and stuff like that are pretty much going to be a 75 kVA or larger. Okay. Which would be the next one. So here's your formula. 2000 divided by 240, 8.3, multiply that by 167. 1.67 gives you 13.92. For 9 amps or greater, here's a 30 kVA. So not quite to those bigger ones, but you might find one like this, a little bit smaller. Greater than 9 amps, what is the maximum primary overcurrent device size permitted for a 30 kVA, 3-phase 480, 208, 120 secondary? Okay. So here's one of those little bit bigger ones I was telling you about that you'll typically see. 30 kVA or 30,000. Here's your formula, how it shows you. 30,000 divided by 480. Oh, I got to add that 3-phase in there. Don't forget that. So 480 volt times 1.732. After you divide it, you should get 36 amps. 36 amps at 125% is 45 amps. Is that a standard size breaker? It sure is. What if that would have said, what if it would have been, say, 46.5 amps? Can I go up? I can now. So what size would I use if it was 46.5? I can go to a 50. Okay. Does that make sense to everyone? Again, this is just my primary protection right here. That's not this one right here. Okay. These conductors and that come in a little bit later. The 45 is a standard size 240.6a. There's just showing you it again. (36 at 125, 45 amps, standard breaker. Okay, another one. Example number one, what is the maximum primary overcurrent device size permitted for a 45 kVA three-phase 480 to 208 120, 50, 60, 70, or 90? Same thing, got a 45 kVA, 45,000 divided by 480 times 1.732, I get a 54. 54 times 1.25 gives me 68. Is that a standard size breaker? No, what's it fall between? So it goes 60, 65, 70, right? So I can bump that up to a 70 amp protection right there. 45 kVA might be real typical what you see. It all depends on what they're looking, how many amps they're wanting over here, really. So how many amps do I have over here? Anybody know how to solve for that? Power in equals power out. So if I've got 45 kVA, what was my secondary? Did it tell me? 208, right? So 45,000 divided by 208 times 1.732 gives me what? How many amps am I going to have over here?
$156.13.
A little higher than I got. I got
Is that-
125.
That I times the 125%.
So I take 45,000 divided by, instead of 480, I'm gonna put 208 right here times 1.732, and I get 124.9. Can I use my
So-
ratio to do it? Oh, go ahead. Who had a question?
So you didn't times it by 1.25% then on that other
I
one?
did. I took 208 because I want to know the secondary amperage.
Right.
I took 208 times 1.732 and divided it by that, or 45,000 divided into it.
But on the, and then you get 125, right?
124.5 or something like that, and I ate.
But you didn't, so do you not times it by the 125%?
I didn't, no. Because I'm just doing power in and power out. This is my power in. So I gotta have that same amount out, so I've only got 54 amps, right? I can use my ratio if I know what my ratio is, okay? But I don't know. If I gotta use, phase voltage, so 120, 208, or 208, 120. I don't know if this is delta. I could say this is delta, so I got 480 volt phase, 480 volt line, 208, 120, so I'd go 120. It's a 4-to-1. So 4-to-1, so if I go 54 times 4. Yeah, 216, so that don't work. I'm guessing it's probably a YY 277 divided by 2.33 times 4. Yeah. Well, I'm guessing it's a Y primary, Y coming in and a Y going out, 120 or 208, 120. So if I go 277 divided by 120, I get 2.3, multiply that by 54, I get 124.65. Okay. So I can use it if I know what the phase voltage is on that, and I'd be willing to bet it's a Y. Okay. So 70 amps there. So 45,000 divided by 480 times 1.732, 831.36, 54 amps. I am allowed to go up. After I multiply it by 125.68, I can go to 70. No, 1. Okay. Next one, a little bit bigger. 75 kVA, 3-phase 480 into 208, 120. 100 amp, 110, 125, or 175. Pretty much doing the same thing. 75 kVA, 75,000 divided by the 480 times 1.732 gives me 90 amps. 90 times 1.20 or 1.25 gives me 113. Next size up, because I'm over 9 amps, is 125. That would be max. That's as max I can go. Okay. Is there a 120 amp breaker? 240.6?
No.
Goes to 1 or 1 to 125? According to 240.6. Yeah, 110, 125. I knew there was something in there. Okay, here's another one, 112.5 kVA. Okay, how many places would you see this? This one right here is going to be real common. Okay. How many amps do I have on the secondary there? I bet I'm close to 200. Or actually more than 200. So this, I'm just feeding it with 125 amps here. I bet this panel is probably a 225, 250 amp panel at 208, 120, which would be common. You'll see that in a lot of buildings. Okay. So this one, we just bumped it up to 112.5 kVA, 480, 208, 120, same thing. 112,500 divided by the 480 times 1.732, I get 135 amps. Times 125%, 169 amps. I'm allowed to go up to the next standard breaker. Is there a 170? Does it go 150, 170, 175, or 150, 175? 150, 175, I do believe. Okay. That's a larger transformer. The next size up rule is not permitted for the transformer secondary conductors. Okay. So I have to have those conductors got to carry that full amperage. Okay. So we'll get into that. Any questions with this stuff right here? You will see this out there in the field. Okay. You will see this. Primary overcurrent only. It does not mean I have overcurrent protection here. This is primary only. Does not mean this one is. Okay. So the next size up does not permitted for transformer secondary conductors. Secondary conductors up to 10 feet long are permitted when they comply with the following. This is straight out of the code book in Article 240. Secondary conductors up to 10 foot long are permitted when they comply with the following. 1, the secondary conductors must have an ampacity of not less than that would be C, 21C, C2. Okay, right out of the code book, 240.21C2. A and B, the calculated load in accordance with Article 220 and the rating of the secondary overcurrent protection device where the tap conductors terminate. It's kind of weird how it reads there. Not less than the rating of the equipment containing an overcurrent device supplied by the secondary conductors, or not less than the rating of the overcurrent protection device at the termination of the secondary conductors. Okay. So now we're talking about these conductors right here. Coming off the transformer secondary up and into this right here, this overcurrent device. Okay, and not over 10 foot long, not over 10 foot long, which is typical. You'll see that quite a bit. Okay, so what size conductors do I need? What size secondary conductor not over 10 foot is required for the 30 kVA 3-phase 480 120 208 transformer that terminates in a 110 amp main breaker? So 30 kVA 208 3-phase. Does everybody see how he gets the 83 amps? Can I take 30,000 divided by 208? What's 30,000 divided by 208? Is it?
144.2307692.
Okay, so what I forget so 208, I have to use the phase voltage, right? We've talked about this 2 weeks ago and a little bit earlier. Phase values. So if I've got a 208 120, 208 is my line voltage or phase voltage? Line. 208 line to line. Okay. That's not going to show up. So 208 is 3-phase, phase to phase. My line phase line is my line voltage phase to phase. My phase voltage is what? Tells you right here, right? Line to line, line to neutral, which would be phase. So it's 120. So I got to use that value. So in order to get that, I have to do, see if it's the next one. No. Basically, that right there. But I'll use 208 and the 1.732. So I can go 30,000 divided by 208 divided by 1.732. So if I use the parentheses, 30,000 divided by parentheses 208 times 1.732 parentheses equals 83.274. Okay, so don't forget that square root of 3, 1.732. So I've got to have conductors that will carry 83 amps. 310.16, what size conductor do I need? I want copper, 75 degree.
Four gauge.
Number 4 is good for 85 amps, but my overcurrent protection device is 110.
So the 2 gauge.
So the number 2, which is rated at 115, right? If I did not have this breaker right here, I would have to stick to the 83 amps. But if I go back to right here, I have to comply with both of these. Like it says in 2, shall comply or does not exceed 10 feet and complies with all of the following. 1, ampacity of secondary conductor is as follows. A, not less than the combined calculated load on the circuit supplied by the secondary conductors, which is 83 amps, right? And B, not less than the rating of the equipment containing an overcurrent device supplied by the secondary conductors, or not less than the rating of the overcurrent protected device at the termination of the secondary conductors. So it tells me I have a 110 amp main breaker. So I've got to be at least that. Do I have any conductors that are 110? According to 310.16. I do not, right? I go from a number 3 at 100 amps to a number 2 at 115 amps. Like it says here, number 2, 115 amps. Oh, I do have to do the 125, which is 104. So I forgot that part. Because I am over, go back to back to 450.3B primary and secondary protection. So secondary protection is 125%. So that's where they're getting that 104 amps. So I've got to have 110 amp protection. Does that make sense to everyone? So now I'm using both secondary and primary protection. Okay. Did I just lose everybody or does that make sense? Everybody at home doing okay? Can't see you, but hopefully you gave me the thumbs up sign. Okay, so let's do another one. What size secondary conductor not over 10 feet is required for a 75 kVA 3-phase 480/12208 transformer that terminates in a 300 amp main breaker? Okay, so now I'm still using 450.3B primary and secondary. What size wire do I need? So 75 kVA divided by 208 times 1.732 comes out to be 208 amps, right? 75,000 divided by parentheses 208 times 1.735 parentheses equals 208.185 amps. So 208 amps. I take that, multiply it by 125%. So go look at table 450.3B. Secondary protection. Why am I not using the 167% on secondary protection instead of the 125?
It's more than 9 amps.
It's more than 9 amps. The 165% is current less than 9 amps. Very good. Anything over 9 amps, 125%. So 125% of the 208 gives me 260. Because there is a 1 next to that 125%, I am allowed to go to the next standard size breaker. Which would be what? 240.6. This is just copper wire. .6 tells me it goes from a 200 to 225 to 250 to 300, right? There is no 275 amp breaker. Is that right? Or to table 250. Is that right?
Yes, it
There's
goes
no-
straight to 300.
Okay, 250 to 300. So a 300 amp breaker is permissible. And so 300 amps, according to table 310.16. A 300 is good for 285, which does not work. I got to use a 350, which is good for 310 amps. Does everybody see that? Does that make sense to everyone? Again, this is something you will see out in the field. Okay, a lot of the times, if it's a commercial project, the plans are engineered, it'll all be taken care of for you. You just got to go look at the plans and it'll tell you, okay, my conductors from this transformer to here are this, breakers that, yada, yada, yada. But if you ever question your engineer, it's a good way to go. I think it gives you one more. Nope, it doesn't. Okay, so when sizing the primary protection only for transformers 1,000 volts or less, make sure to use table 450.3B, calculate the primary current, and then determine which column to use, table 450.3B. Sizing the transformer secondary conductors couldn't be any easier. Simply select the secondary conductor with the ampacity equal to or greater than the secondary protected device ampere rating in accordance 240.21C. Please use the 23 code book and exam prep textbook to answer the review questions. Okay. So you will have some questions out of 450, okay? Probably not as much as what I did, but you will have some. They should be pretty much word for word right out of the code book to find them. I do know one of them was in regard with .14. Okay. I do remember that. I had to go look that one up because I didn't know if it had the class 2 and class 3 transformers in that section. Okay. Any questions regarding what we went over in the Delmars? Okay. There probably will be a couple of questions on those different types of transformer connections. Make sure you read through there, find them, know that they're there. Go over them. Should be pretty much word for word right out of the book. Go watch these other videos. Right here. Go watch these other videos. To see about those. Unit 28 and NEC 450. If you have any questions, reach out. I will be busy on Friday. So I probably won't get to you Friday because I will be busy with family doing stuff and with Halloween. Go have a good, fun, safe Halloween with your kids if you have them. And we will see you all next week.
Wait, Todd. Can you hear me? Okay, am I in the right chapter here?
No, we are not in that book.
This code book?
That's the illustrated guide to the code book. You want either this or part of it?
Oh yeah, I've been following around the Delmars. Oh, it's that one.
Actual code book.
Oh, I thought it was the illustrated. My bad.
No, we won't get into that until the first or second week of December.
Oh,
So
okay.
you need the code book.
Sorry,
Do
you
you
cut
have
out right there. Yeah, I do have it. I'm gonna go look for that. I think I have it though.
Okay, if you don't, you'll need it because you'll get some questions out of there.
Okay, thank you, Todd.
Yep. Right here.
Yeah, just right there. How often do you check your messages?
I usually get a notification on my phone or my watch that I got one.
Okay.
If I'm going to reply to them because of bad questions or something like that, I usually do it at night.
Okay.
So,
Just like every night then?
yeah, I usually do.
Okay then.
But yeah, this Friday with Halloween and I got some family stuff in Salt Lake I gotta go do Friday. I probably won't do anything.
Yeah, I got it.
But Saturday, usually Saturday night or Sunday late night, I usually do.
Free then?
Yeah.
Okay then.
All right, any other questions from you guys left on here? If not, we'll see you all next week.